All right, so let's go ahead and discuss the method of moments. So first, a couple of definitions. So we define the kth sample moment. This is about 0, to be the random variable mk prime, which is 1/nth of the sum of your random variables corresponding to your observations raised to the kth power. So this is the kth sample moment is a random variable. Of course, when you make some actual, this is the random variable, you make some actual set of observations, and what you get is a number, which is denoted little mk. So this would be the sum of, that's supposed to be a 1 there, 1 to n of your little x sub I of k's, where these are the particular observations. So these are, a set of observations, so these are actual numbers that you might get, and then you would call, by abuse of language, this would be your kth sample moment. Okay, so now what's the utility of these? Well, these are estimators for the actual moments. So if you remember, I think we had defined these before. The kth moment about the origin is the expected value of x sub k, where x is some random variable having the population distribution with distribution of the population. So in this, what I'm implicitly saying, I should have mentioned it explicitly, all these xi's, of course, being your observations, these are all IID random variables with some unknown distribution that describes the population, some f theta of x. And, when I use this capital X, I'm just saying some random variable with that distribution. So these are the moments of that distribution, if you will, mu sub k primes. Okay, so now it's just kind of a tautology that these capital M sub k primes are unbiased estimators of the of these population values, these moments of the population, the kth moments of the population. But what we'd like to do is then use that to produce estimators for parameters of our population. So for some particular thing. So it's possible. I mean, if we wanted to know, if somebody said, what is the first, second, and third moment of the population, and then what we could do is use these things, and they'd be a nice, a reasonable choice with some unbiased estimators for moments of the population. Of course, that's not typically what happens. I mean, let's imagine that we, for example, are given an exponential population, and let's say we've decided to represent it in the form f with an unknown parameter lambda of x is lambda e to the minus lambda x. And then we might say, well, how can we estimate the parameter lambda? This is a little bit more reasonable. Lambda is not a priori given as some moment of the population. So what is it in terms of the moments? So the method of moments is, let me just kind of say it first. Method of moments is we solve for unknown parameters in terms of moments, and then the solution gives estimators for the parameters. Okay, so let me just give an example really quick. So in the exponential case, this is a very silly example, by the way, as we'll see. But in the exponential case, if we look at the mean, so you might recall or just check it, the mean of the population is given by 1 over lambda. And so we know that our first moment about the origin, which if you look at it by this formula here, is actually just the mean. I guess I pointed the wrong formula, right? So this thing for k equals 1 is just the mean, and so we know that we have that our what do I call it, m sub 1 prime, which in this case is actually the sample mean, is an estimator for mu, and that's going to tell us that 1 over this guy, 1 over x bar, is going to be our estimator for 1 over for lambda. Okay. Now, how good is that as an estimator? It's actually a little bit problematic, which I'll mention in just a moment. Of course, you might realize that if I wanted to, I could have, instead of using this representation, lambda e to the minus lambda x, I could have used this representation, making the substitution that theta is 1 over lambda, and call this 1 over theta e to the minus x over theta. If I use this representation, then I find that the mean is theta, and therefore x bar is an estimator for theta, and it's an unbiased estimator because we actually know that because theta equals mu, because we know that the sample mean is an unbiased estimator for the mean. Is 1 over the sample mean an unbiased estimator for 1 over the mean? It is biased, actually. This thing is biased, as we'll see. But maybe before we, so I do want to explain why it's biased, but before we do that, let's mention a slightly less trivial example. How about if we had a gamma population, for example? Of course, the exponential population is a particular example of a gamma population, but in general, a gamma population has 2 parameters, which makes it a little more interesting as an example for this kind of thing. So let's see so we'll use the following representation. So we'll say our population is given by some function with unknown parameters alpha and beta of x. So here I have a couple of thetas, so to speak. And what is this formula? This is proportional to x to the alpha minus 1 e to the minus x over beta. We're taking over positive x like we were before, but I forgot to mention. And we have to have a normalization factor to make this integral 1, and the normalization factor is 1 over b to the alpha, and the famous gamma of alpha, the gamma function from whence this gets its name. But what's going to be useful for us to keep in mind in this particular case is the formulas for the mean and the variance of the gamma distribution. So let me just go ahead and remember quote unquote, or look it up, that so if you can look up the moments of this. So the first moment of this distribution, the first moment of the gamma distribution is alpha beta, and the second moment, the expected value of the variable squared, it happens to be, in this case, alpha times alpha plus 1 times beta squared. Okay, so these are things that we could solve for. So this is the expected value of x squared, which we can just describe in terms of the variance and the square of the mean. Okay. So let's suppose now we have that information. We want to find estimators for alpha and beta. So I'll just mention, by the way, that in the case alpha equals 1, we're actually talking about the exponential variable, but let's kind of do this thing with 2 parameters. Okay, so so in this case, what do? We say, well, we know how to get a good estimator for the first and second moments. Those are going to be these M1 prime as an estimator. You know, this is the sum of this is the sample mean, and M2 prime, sum of the xi squared, is going to be a good estimator for mu2 prime and for mu1 prime. And so altogether, I see that, well, if I can solve for alpha and beta in terms of the mu1 and mu2, then I can move along. So I don't know. This is just a little bit of algebra here. Let's say I solve for I don't know, solve for alpha in the first one, for example. So the fact that mu1 prime is alpha beta tells me that alpha is mu1 prime over beta, which I can then use to substitute in my second expression. So I get mu2 prime is alpha plus 1 beta squared. Now let me substitute in for alpha. I get mu2 prime is blah, blah, blah. Let's see, mu1 prime over beta. Mu1 prime over beta plus 1 beta squared. And now let me go ahead and simplify that a little bit. So what do we got? Mu1 prime quantity squared over beta squared plus mu1 prime over beta, all that times beta squared. And I get mu2 prime is equal to mu1 prime squared times, the betas cancel, plus mu1 prime times beta. And that tells me how to solve for beta. So I get that beta is equal to, you take your mu2 prime, you subtract off your mu1 prime squared, and you divide out by mu1 prime. Okay, that gives me a solution for beta. Similarly, you can play around and solve for alpha. So I'm getting tired. I'll just tell you what the answer ends up being. So alpha, in terms of these estimator, in terms of these moments, turns out to be mu1 squared over mu2 minus mu1 squared. Okay. So similarly, and what does that tell us? So the method of moments says that now that we've solved for our parameters in terms of our moments, why not have an estimator beta hat for beta, which we'll define to be the second moment. So I'm just going to really just taking this formula and replacing the moments by the corresponding estimators. M1 squared over M1 prime. Alpha hat is M1 squared over M2 prime minus M1 prime squared. Okay, so there we go. We have a couple of estimators. So these estimators that you get, as we've kind of alluded to a little bit, they're not unreasonable perhaps, but they tend to be biased. I want to explain why that first one was biased, which I stated but I didn't explain. They tend to be biased, but they do tend to be at least consistent with some kind of mild hypotheses. These things do give consistent estimators. Okay, so let's just to see how these kinds of how could I have told that this thing was biased? So this is the first kind of silly example that I came up with the exponential population. Excuse me one second. So this is one silly example that I used with the exponential population. And we got this this estimator 1 over the sample mean to describe this unknown parameter lambda, which actually was 1 over the population mean. So just as a fun side topic, y was 1 over x bar a biased estimator for lambda, which turned out to be 1 over the population mean. One moment. So there's a little bit to say here. The technical tool that we're going to use is kind of just a fun side topic in itself, and that is Jensen's inequality.